Good morning, good afternoon, and good evening. Let's start chapter 18. We just finished up talking about plants and fungi. Remember, we're doing what we call the survey of life. The survey of life, we began with the simplest organisms, bacteria and archaea, and then we made our way up to the more complicated organisms, eukarya. Remember, three domains: domain bacteria, domain archaea, domain eukarya. Within domain eukarya, there are four kingdoms. Those four kingdoms are plants, animals, fungi, and protists. Protists were the first eukaryotes we talked about. Then we talked about plants. Then we talked about fungi, and now we're to our last kingdom. And our last kingdom is Kingdom Animalia. Remember, if you remember how life is organized, we have domains, kingdoms, phyla, class, order, family, genus, species. And we said to imagine that the domain is like a continent. And so there's 7 continents. Which continent do you live on? You live on North America. A kingdom would be like a country on that continent. So how many countries are on the North American continent? Canada, U.S., Mexico. The kingdom is, which country do you live in? You live in the U.S. And as we go further down, we go down, kingdom phylum would be like what state do you live in. Class would be like what county do you live in. And for some of these organisms, we are going to go as far down as class. All right, so domain eukarya, kingdom Animalia. What requirements, what do you have to be an animal? The group that led to animals probably split off from an amoeboid relative about 1 billion years ago. After the Cambrian explosion, remember at the end of Biology 1, we talked about what we call macroevolution, and we talked about how the end of the Precambrian was with a huge extinction, and then right after that is the Cambrian explosion of new species. This increased animal diversity, this happened about 535, give or take, million years ago. MYO. Billion years ago, million years old, but million years ago. Cambrian explosion, lots of new species. Almost all of the species alive on the planet today can trace their origin to this time. This is a picture of animals that probably existed somewhere around the Cambrian explosion. There are an early core date here. I'm not sure if you can see it very well. When you get a chance to look at that, it almost looks like a fish. But it by far is not the most complicated animal in this picture. The most complicated animal in the picture is Animalicaris. Animalicaris was probably the apex predator of the time. It was basically a giant swimming bug, probably 2 to 3 feet long. Interesting thing about Animalicaris, the way fossilization works is that only the hard parts get fossilized. And because only the hard parts get fossilized, very rarely you get soft parts, which will fossilize. So what happened was Animalicaris was actually believed to be more than one animal because they would just find the bits. This center mouth region thing is very hard, and so that would fossilize a lot. And at one point, it was believed to be one particular species, just the mouth parts. And then these tentacle things that came off. Imagine one of these things dies and it gets ripped apart by other predators, and the parts are scattered to the 4 winds, right? Well, they were believed to be separate species, and it wasn't until one whole intact one was discovered as a fossil that we finally figured out, it's like, oh, all of those separate things that we thought were different animals are actually part of one animal. Animalicaris, really, really cool looking critter. Here is a worm, probably some ancient annelid. And then this one right here, hallucigenia. You have to look at hallucigenia on your own. Do a Google search for hallucigenia. We're not really sure what hallucigenia was. That's why the name means hallucinogen. It means crazy vision. It means something that shouldn't exist. We're not exactly sure what hallucigenia was. We're not exactly sure how it moved, if it moved. If you ask me, and maybe I'm very, very wrong, I wouldn't be surprised if this wasn't a situation like Animalicaris. in that this is just a body part of something, and that we don't know what the rest of it was around it because it didn't ever fossilize. These animals obviously don't exist today. What has happened? The Earth has moved on is what has happened. Remember, we talked about evolution. We talked about how small changes over time lead to big changes over great periods of time, and those big changes change a species from one species into another. So, what structures, what features, what characteristics do you have to be considered an animal? And the first is you have to be multicellular. To be an animal or a plant, you have to be multicellular. Most fungi are multicellular. But again, you have to be multicellular to be an animal. You have to be heterotrophic, which means you don't make your own food. Hetero means different. Troph means food. You have to be heterotrophic. You have to eat food. You have to find other things. You cannot make your own food. You must develop from an embryo. You must be motile. You must move. And that is a little debatable, and we'll talk about that as we get there. Not all animals move a lot, but all animals have at least a motile, a mobile life stage. As we said, with being heterotrophic, animals have to ingest food. They don't make their own food. They're not like plants. They're not autotrophs. They are heterotrophs. They don't make their own food. They must eat food. Most of them have tissues and organs. We'll talk about that when we get there. And there's between 4 million and 30 million species of animals. And that is a big range. What this means is, okay, there's about, give or take a few 100,000, about 1.5 million described animals. I want you to understand what described means. What it means is more than one representative of the species was caught by a scientist. It was compared against all other known species and found that it hadn't been caught or described before. So then this scientist wrote down all the vital details of this particular species in a paper and then passed it around to experts in that field. If you found a new bug, they send the paper to other bug researchers. If you found a new fish, they send it to other fish researchers, people that are experts in that group. And then they look at your work and they say, you know what, you're right. This is new. We haven't seen this before. And then they publish it. They give it a name and they publish it. That's what described means. And there's about 1.5 million, give or take, described animals. There's about 1.8 million described species total. That's plants, animals, fungi, bacteria, all that stuff. About 1 million-ish, 1.5 million-ish described species of animals. So 1.5 million, that is not even half of what this guess is down here. There's between 4 and 30 million species of animals total on the planet. And the question is, well, number one, why is the range so big? And number two, is this really just a shot in the dark? Is this just a random guess? It's not a random guess, but it is a guess. Because how do you know how many you don't know? Well, the way you do it is you look at how quickly you are discovering new species. How easy is it to discover new species? If you imagine that you're going to be looking for all of the new species that there are, and as you approach the halfway mark, what should start happening to your rate of discovery? If scientists go out every day looking for new species, and they find these new species, and they do all those steps I talked about describing a species, they go through all those steps, what should happen as we approach, what should happen once we pass the halfway mark, what should happen to the rate of discovery? If we found half of all there are to find, the rate of discovery should start decreasing, because it should be harder. It should be harder to find new species if we've already found most of them. So you look at the rate of discovery, and then you do some really rough math. And the rough math is where we get this between 4 and 30 million. And the honest answer is probably somewhere in between there, maybe somewhere around 10 million. So the rate of discovery gives you an indication as to how many there are based on how quickly we're finding them. So when we look at the rate of discovery, the real question is, well, what is it doing? Is it going up or is it going down? And the answer is it's going up. The rate of discovery is increasing. We are finding more and more new species every year. That is how we get this guess of how many species there are.